us about chiral color codes.
Yeah, thank you so much, Steve. Today I'm going to talk about chiral color code, which is a new types of stabilizer code that we can obtain by gauge fixing the 3D gauge color code. And I think there is still some interesting application for this code for the quantum information processing. So if you have any questions or something's not clear, then just interrupt me and feel free to ask any questions. So I would say that now we all agree that topologically ordered system is a great platform to do quantum computation. And I think there exist at least two reasons for this. The one is that since we encode our logical information in the global degrees of freedom, which means it has some it should be intrinsically robust to some local noises, which expect to be some errors in our physical real world. But another reason, which is more interesting for me, is that we can borrow some knowledge from the condensed matter physics, and we can use some knowledge about the SPT phases and defects which the topological system supports to reason about what kind of fault-tolerant logical gates can realize in these systems. So it's great. But actually, if we really try to use this topologically ordered system to do quantum computations, then there exists one problem which seems to be very intrinsic to this topological system, which is it is very fragile to measurement errors. So what do I mean by that? And to understand this, I think the simplest way is to think about the simple example. So let's think about the decoding process of the 2D toric code. So we measure the checks over there. Then let's assume that we get some syndromes like this. But there was some errors in the measurement process, and some of the syndromes are actually faulty. And if we try to naively decode the code, then what we're going to do is we connect the syndromes, then actually it grows the physical errors. And we can easily convince that the growth of the physical errors are actually unbounded if there exists a tiny amount of the measurements. And we can also think that this is kind of intrinsic properties of the topological codes with the string operators. And one way to avoid this problem is actually to measure the checks a lot of time to confine the measurement errors and then do error correction. But this method has obvious problem because it increases the time overhead. And also now we have to decode in 3 dimensions, so it increases decoding complexity. Also, it can introduce some time correlated errors. So we want to do better than this. So the fundamental questions that we want to ask at this point is if there's a way to decode the topological codes by just a single shot of the measurement, even when there exists some measurement errors. And the answer for this question was actually given by the Hector Bowman in 2014. And his answer is to use subsystem code error correction. And he gave the nice example of the 3D gauge color code, which can be used to decode the 3D color code by a single shot measurement, even when there exists the measurement errors. And these single shot error correction properties are actually closely tied to fault-tolerant code switching between the stabilizer code in this gauge group of the 3D gauge color code. For example, we can code switch between 2D and 3D color code by a single shot. So this was the first examples of how to do fault-tolerant reversal quantum computation using the topological codes. And then a few years later, another great example was given by authors here, and I think 2 of the authors are actually in this conference. And they actually showed how to decode the 3D normal toric code by a single shot by showing there exists some subsystem codes containing 3D toric code. And this construction can be generalized to the qudit cases as well. But so far, it was not clear how to decode the topological codes that goes beyond the toric code. And this is the question that we want to answer in this talk. So the first part of the talk, I will show actually there is a model in 3D gauge color code that realizes various topological orders which goes beyond the 3D toric code. More specifically, for qubit cases, the model realizes the 3D fermionic toric code. I will explain what I mean by this later. And if you use qudit, then the model can realize the 3D walk-around model with some exotic ZD alpha anyon theories on the boundary. And it turns out that these anyon theories can be used as some building blocks to realize some other abelian theories. And we expect that these ZD alpha anyon theories actually realize all abelian anyon theories. So yeah, now our model kind of opens a way to study these abelian anyon theories in a fault-tolerant manner. And this anyon theory has some interesting property, which is it has some chirality. It turns out that defining chirality for the stabilizer state is kind of a tricky problem. So in the next part of the talk, I'll propose some quantum information theoretic definition for the chirality and claim that indeed the Chiral color code is chiral in our definition. Okay, so let's start for the first part. So to explain the construction, let us review the 3D gauge color code construction. And I think the key part is the lattice that gauge color code can be constructed. So the lattice requires two special properties. One is the four valent, meaning that each vertex is connected by the four edges, as we can see in this lattice. And the second property is that the lattice should be four colorable, meaning that we should be able to assign one of the four colors to each unit cells in a way that the neighboring cells doesn't share any same colors. So we can see here that we assign 4 colors for each unit volumes. And sometimes it's easier to think about the lattice in the drawer picture. And in this case, in drawer lattice, the volumes becomes the vertices and faces becomes the edges and so on. And in this talk, I will use the alphabet letter A, B, C, D to denote the colors of this model. And for the dual lattice, I will use the lowercase alphabet. And using these colors assigned on each volumes, we can also assign the color to the lower dimensional cells. For example, the face that's shared by the A and B colored volumes, we can assign A, B colors and so on. And we will assign the qubit for each vertices. And then the usual 3D gauge color code has a gauge group, which consists of two types of the placket operator. One is just the Pauli X operator on each placket, and one is the Z-type placket operator defined on each placket. And this is not a stabilizer group because usually this placket operator doesn't commute each other. So it's a subsystem code. But if we think about the center of this model, this gauge group, it turns out to be our stabilizer group is given by the volume operators. So if we do error correction, then our goal is to only correct these volume operators. And then the interesting point of the gauge color code is actually we can gauge fix to the other topological codes in this model. For example, if we measure all Z-type placket operators, then the X volume stabilizers survive. Then we can realize the 3D color code. But if we also measure X and Z-type plackets on the boundary, then the bulk and boundary becomes disentangled. And then all the logical informations are living on the boundary, and we can realize the 2D color code. Okay, now I will show you there's another way to gauge fix to the new stabilizer code. So for the qubit cases, our proposal is like this. So it only has the placket terms, but the assignment of Pauli operators depends on the color of the placket. More specifically, if the two placket doesn't share any same letter, then we assign the same Pauli operators, and yeah, if not, then we assign a different Pauli operators. And because of this assignment, we can easily check that all placket operators are commute. The reason is because all placket operators share even number of the qubits, except the case when they share no colors. But we assign the same Pauli operators, so by construction, they should be a stabilizer model. And yeah, also we can easily convince that this stabilizer group is in the subgroup is the subgroup of the gauge group of the 3D gauge color code. The reason is because we can just obtain these Y-type Plaquet operators by product of X and Z-type Plaquet operator. And if we count the number of logical qubits encoded in this model, it turns out that it encodes the secondary number of the manifold, which is the number of independent incontractable plane in the manifold. And it's kind of interesting because in normal 3D color code, we know that it's equivalent to 3 copies of the toric code. So it should encode the 3 times secondary number of the logical qubits. So it already tells us the model has some different features compared to the 3D color code.
When you say d equals 2, you mean qubits?
Oh, yeah, local Hilbert dimension, sorry, yeah. And it turns out that the model realizes the 3D fermionic toric code. So I'll explain what I mean by 3D fermionic toric code. So yeah, what I mean by this is actually its string operator excites the point-like excitations, which behaves like the fermions. And to see this, the simplest way is to construct a map between Baran operators and Pauli operators in our lattice. So our construction is as follows. So we first assign 4 Baranas for each vertices. And this is always possible because our lattice should satisfy the 4 valent conditions. But 4 Baranas corresponds to the local Hilbert dimension with 4. So to matching the dimension, we have to impose this strong constraint by demanding that if we multiply all 4 Baran operators, then it should be identity. So we will only think of the sub-Hilbert space of the entire fermionic systems. And then after imposing this strong constraint, then we can reduce the local Hilbert dimension from 4 to 2. And then with these conditions, we can map the pair of the Baran operators to the Pauli operators, which satisfy the commutation relation. And if we apply this map to the previous XYZ color code, then it turns out that this Barana toric code maps to the XYZ color code. So is there any questions at this point? Okay, great. Yeah, so now we can easily construct a fermionic string operator with this map. Oh, I think the figure is, interesting. So the way to construct the fermionic string operator is actually we start from some fermionic strings which consist of Baran operators. And then we apply this map to convert the Baran strings to the Pauli operators. I think figure is somehow erased, but. And then we can check that this string operators actually induce a point-like fermionic excitation at the end of these string operators. And the fermionic string operators violates the 3 Plaquet terms at its end. And in dual lattice, it's a bit hard to imagine without the picture, but in dual lattice, it corresponds to the smallest loop in our lattice. So for example, if the fermionic string ends at the edge with the color ABC, then it excites the excitation with AB, BC, AC loops. Oh, sorry, I think something. Yeah, so this is a construction for the fermionic string operators. We start from the fermionic strings, and if we apply the Pauli mappings, then we can construct the fermionic string operators in the XYZ color code. And we can more think about what kind of excitation structures are actually in this model. And the way to do is we first have to think about what kind of local meta checks in this model. And in this model, if we multiply all Plaquet terms on the 8 one-unit volumes, then it becomes identity, meaning that in dual lattice, it realizes the Z2 gauge theory. So this means that all the excitation actually should form a loops in the dual lattice. And this is similar to what happens for the Plaquet terms in the 3D toric code. But it turns out that the physical properties of these models depends on the parity of the loop, weight of the loops. So for example, if the weight of the loop is given by even weight, then we can conclude that it behaves like bosonic excitations as the loop excitations in the 3D toric code. But if the weight of the loops are given by odd, then we can conclude that there exists some fermionic excitations in this model. And recently, it was discovered that the fermionic toric code has a transition at the finite temperature. So we can conclude that gauge color code also contains some topological order that is long-range entangled at the finite temperature.
Sorry, Dongjin, probably a basic question here, but can you just explain again why you need this Majorana mapping? Like, what is this? How does this show you the model?
Right. So, yeah, our model is not CSS code, so it was a bit hard to find what's the logical operator in this model. But with the Majorana language, actually, it's kind of easy to treat our find the logical operators with this model. And if we cut the string operator, then we get the fermionic string.
Okay, so you get the logical operators of the Majorana model, then just map
Exactly.
them.
Yes.
Thank you.
Yeah. And also we can think of the color boundary of this model as the usual 3D color code. And for example, if we impose the A color boundary, then there exist three types of plaquette, AB, AC, and AD. And these plaquette terms can be thought of as the K-type's honeycomb model, but only with the charge terms in the air. And since we know that these plaquette terms consist the anomalous one-form symmetry of the model, so we can conclude that the XYZ color code realize the long-range entangled mixed state on the boundary if we tracing out the bulk. And the reason is because if you have anomalous symmetry, then the density operator should be long-range entangled. Okay, and now let's think about how to do single-shot error correction with this model. It turns out that although all the excitation in this model is actually a loop, but it's not actually true because the smallest loop in this model corresponds to fermionic point-like excitations, which means it has a kind of string-like operators. And we have seen that if there exists a string-like operators, then we cannot do single-shot error correction. So we have to use the fact that the model is in the 3D gauge color code to do subsystem error correction. And the gauge color code only encodes the logical qubit on some special lattice, which has some defects on this model. Here, what I mean by defect is that it violates the four valence conditions at each corners. And if we construct the XYZ color code in this model, then we can observe that there exists the unpaired Majorana zero mode at each model. And if we connect this Majorana zero mode by fermionic string operator, then it becomes the logical operator. And since there exist three different ways to connect the Majorana operators up to stabilizers, and each string operator corresponds to logical Pauli operators. And we found that, yeah, although it's a subsystem error correction, so we can use the normal gauge color code decoders to do error correction, but we also found there exists a way to decode our code without going out from the fermionic phases. And to argue the single-shot error correction, what we have to show is that there is a way to confine the measurement errors. And what do I mean by that? Is that given some measurement syndromes, since we are measuring the gauge operator, so it's a gauge syndromes, we want to make sure that our recovery operator, Pauli operator, should be bounded by the weight of the measurement errors. And this is because we don't want to include the unbounded physical errors induced by the faulty measurements. And if we think about the usual gauge color code decoding process, which first measure all X-type pockets and Z-type pockets. We can think of the process as code switching between normal 3D color code, but with different Pauli operator convention. And physically, what it happens is that we confine the string operator of the one type of the 3D color code by switching the role of Pauli X and Z to the other 3D color code. And we can kind of mimic the similar behavior in this model. So we code switch between two different XYZ color code, but now with the role of Pauli X and Y and Z are changed. And if we code switch between these two stabilizer code without destroying the logical information, what you can see is that the fermionic string operator in one model is actually confined in the other fermionic string, other XYZ color code. And it satisfies the linear confinement property. So by matching the gauge syndromes, we can do single-shot error correction. And we can also think of this process as a new 3D gauge color code decoder. Okay, and now we can generalize the construction for the qudit cases. And to generalize the construction, we have to define so y-like operator for the qudit. But the y-like operator is not unique for the qudit cases. So we had to introduce the chiral parameter alpha. And then we can generalize the construction by replacing y to x times z to the alpha power. But it turns out that the phase of the model dramatically changed, depends on the local Hilbert dimension d and chiral parameter alpha. So yeah, but this model is still the stabilizer group, stabilizer code, and it's in the gauge group of the qudit gauge color code. So it inherits all the fault-tolerant features from the qudit gauge color code. But the phase depends on the d and alpha. So when d is odd, it actually turns out that the bulk is not topological, meaning that it's not a topological code. And we could actually show the bulk is short-range entangled. But when d is even, then the phase depends on whether d is divisible by 4 or not. And if divisible by 4, then bulk realizes the normal qubit toric code. But if not, then it realizes the fermionic toric code as we've seen before. We can also think of what kind of anyon theory it realizes on the boundary. And it turns out that it realizes the ZD alpha anyon theory, which can be chiral. It depends on the parameter alpha. So I will explain this point. So the later part of the talk, I'll try to unpack this statement. Okay, so I think the first step that we can do is actually go back to how the excitation structures changes in this model. And this model also has local meta check for each volume, meaning that it should form all the excitations should form a loops for the qudit cases as well. But it's not a ZD gauge theory anymore, and it's more depends on the structure of our lattice. So the simplest way to form a loop in our lattice, in dual lattice, is just we repeat the -1 and 1 on each dual edges and then form a loop. But it turns out that the parity of the weight of the loop should be always even to satisfy these local meta check conditions. So it's kind of different from the qubit cases where we could have 3 triangular loop-like excitations. So it kind of implies that there might be no point-like excitations in this model. And it turns out that when the d is odd, then such solutions doesn't exist. And we could also show that when local Hilbert dimension is odd, then all the string operator is confined. So there is no point-like excitation in this model. But when local Hilbert dimension is even, then actually there is a way to construct this unit triangular loop, which is just assign d/2 to each model. If we add these 2 syndromes for each vertices, it becomes 0 mod d. And so in this case, we have string-like operators. And the physical properties of this point, like excitations, depends on whether D is divisible by 4. So if D is 0 mode 4, then it realizes the bosonic toric code. If it's a 2, then it realizes the fermionic toric code. Yeah, so we saw that there is no string-like operator in this model, so it hardly implies this model is actually short-range entangled. And so, but we want to prove the statement. And what do I mean by short-range entangled state is that we expect there exists some local quantum channel that prepares the ground state of the Chiral color code starting from the product state. And you could actually construct those local quantum channel explicitly, and we use the kind of error correction process to construct the local channel. So the process is we first measure all the plug test syndromes from the product state, and the measurement can be done by the local channel. And then our next goal is to fix the random syndrome outcomes by the local channel, and this process can be done by the confined string operator in this model. So if we combine these two local channels, then we can prepare the ground state of our model. And we can think of, on the boundary, what kind of anyon theory arises. And it turns out that there exists the ZD alpha anyon theory in this model. So what is ZD alpha anyon theory? It's a subtheory of ZD toric code, where its fusion rule is given by ZD cyclic group. And the group is generated by E times M alpha anyons, where E and M is the electric charge and magnetic flux of the ZD toric code. And then we can compute the braiding and self-statistics of this model. And it turns out that sometimes this model realizes the non-zero chiral center charge. So we could conclude that the Chiral color code realizes the 3D walk-around model where its boundary ZD alpha anyon theories are living. And the reason why we had topological order the case when D goes to even was that this ZD alpha anyon becomes premodular, so it can actually enter the bulk without any excitations. Okay, this was the first part of the talk. So we now see how to construct some new stabilizer code in the gauge color code. And then we show that it realizes the fermionic toric code for the qubit cases. And for qudit cases, it realizes some exotic topological phases. It depends on the local Hilbert space dimension and some parameter alpha. And the second part of the talk, I will switch the gear a little bit and then try to claim our model is actually chiral. So to claim the chirality, we actually borrowed the concept of chirality from the condensed matter physics. So we studied anyon theory, and we computed the chiral center charge, and we claimed that since it's not zero, so our stabilizer state is actually chiral. But this argument seems to have some problem. The reason is because our anyon theory is living on the boundary of the 3D manifold, but the physical meaning of the chiral center charge is given by the chiral edge current induced by the temperature difference. But the boundary of 3D manifold doesn't exist, so the physical meaning of the chiral center charge in this case will be vague. But there has been many proposals to actually study the chirality just by the bulk wave function. And I think one of the most successful measure for the chirality was the modular commutator. So to compute this quantity, what we need is only the density matrices of the bulk. And then we compute the marginals of the whole system and compute the modular Hamiltonian. And if we compute the expectation value of the commutators, then it sometimes captures the chirality. So this is the one way to argue about chirality of the bulk wave function without the boundary. But if you apply this definition to the stabilizer state, then it turns out to be problematic because stabilizer state is too simple. And if we naively compute the marginals and compute the modular commutator, then it always gives a 0. So there's no way to capture the chirality just from the bulk density matrices for the stabilizer state. But it seems that our anyon theory has some chirality. So we try to argue, we start to think about how to really argue our stabilizer mixed state is chiral. And to this, we came up with new definitions for the chirality, just using the density matrices. So our proposal is that since we call the system is chiral when the system lacks the time reversal symmetry, so given some density matrices which describes our physical system, if there's no unit trace that maps rho to rho star, which is a complex conjugation, then we can say our system lacks the time reversal symmetry, so we may say it's a chiral. But of course, this definition has some problem because we can always find such U for any density operators. So we need some restrictions for U. And one definition is inspired by the condensed matter community, which is we just demand the U to be finite depth unitary, and if such U doesn't exist, then we may say that the density operator is actually LU chiral. And in this definition, we don't need any Hamiltonian, but we just need a density operators. And if we can claim that there is no such unitary, then we can say our quantum state is chiral. And another definition was actually proposed last year by these great authors. And they demand that this U to be tensor product of some n-partite systems. And we can find that there is no such unitary that maps to rho star. Then we can say that it's n-partite chiral. And we'll use these two definitions to argue that the boundary of the Chiral color code is actually chiral. And one point is that with these definitions, since we can just change the basis by the depth 1 circuit, so the complex conjugation doesn't really depend on the choice of the basis. Okay, and then we obtained the two results. The first result was that if the ZD1 stabilizer mixed state is not isomorphic to ZD-1 anyon theory, here what I mean by isomorphic is there's no isomorphism between this anyon theory, then we could argue that the mixed state realized in the boundary of this model is LU chiral. And using some elementary number theories, we could classify when does this non-isomorphic properties holds. And it turns out that if the local Hilbert dimension is given by p to the m power, where m is 3 mod 4, then this property holds. So we could say the stabilizer mixed state is LU chiral. And this definition turns out to be very interesting because there exists a case when the anyon theory has a 0 chiral central charge, but it's still LU chiral. So there is some kind of mismatch between the condensed matter, the definitions, and our quantum information theoretic definition. And our second result is that to stabilizer mixed state to be 4-partite chiral, it's enough to, the underlying anyon theory should be non-isomorphic to the ZD-1 anyon theory. But it turns out that there's no 3 partitions that our stabilizer mixed state becomes the chiral.
Is that anyon theory like non-chiral that does not have a gap boundary?
Oh, that's a great question. Actually, it has a gap boundary for the Z91 cases.
Okay.
But there is also example, like Z51 cases. It's chiral central charge is 0, and also it's not LU chiral, but it doesn't have gap boundary. So it seems to be, yeah, some different definitions. And I will now explain the proof sketch for this statement. So the main idea is to show that anyon theory is actually invariant under the finite depth deformation. And this statement sounds to be trivial, but actually to prove this, it turns out to be not that easy. So given some systems, the way to compute the topological spin is we just compute this expectation value of the sequence of the operator. And physical meaning of this sequence is we just swap the particle here and here, and then see what kind of phases we get after swapping. And so if it's a -1, then it's a fermionic, but in general anyon theories, it can be any complex numbers. And then we assume that there exists a finite unit tree that maps rho to rho star. That means if we take the complex conjugation, the left and right side, and then by applying the rho, we can obtain some flattened string operator, which has the inverse topological spin. And then if the underlying anyon theory is not isomorphic to the ZD-1 anyon theory, then we could actually see that this kind of string operator cannot exist by some local recovery argument. Since there's a stabilizer state such that ZD1 and ZD-1 anyon theory is not isomorphic, so yeah, there is a stabilizer state which is LU chiral. For the four-partite chirality, we use basically same technique, but we need to come up with new techniques to define what we mean by anyons when the unit trees doesn't need to be finite depth. So we came up with the four partitions where we can concentrate the excitations on the boundary of the partitions. And then we could assign the topological spin of the each edge charges without ambiguity. And then we could use the techniques that we used for the LU chirality to show that there exists no such four-partite unit tree that maps rho to rho star if the underlying anyon theory is not, underlying anyon ZD1 theory is not isomorphic to the ZD-1 anyon theory. So this implies that to stabilize our state to be chiral, we need at least four-partite entanglement structures. To claim there is no three-partite partitions which rho to rho star unit trees doesn't exist, it turns out to be quite simple because we know that all three-partite stabilizer state can be distilled to EPR pair or GHZ type entangled state, which neither is a chiral state. And this actually consistent with the fact that the modular commutator, which is defined on the three partition, doesn't capture any chiral stabilizer state. Okay, so here's the conclusion of the talk. So in the first part of the talk, we show that there is a way to gauge fix the 3D gauge color code to topological stabilizer code, which realize the fermionic with chiral topological order. And so we hope that these phases can be now started for the quantum information processing purposes. And to argue that the stabilizer state is actually chiral, we need to come up with some new definitions what we mean by chirality for the stabilizer states. And we show that the boundary of the chiral color code realizes the LU or four-partite chiral states. And there are some open, interesting directions. So we couldn't find, we expect that there exist hidden symmetries in this model, which is related to the transversal gates that we can realize in this model. But unfortunately, we couldn't find any symmetries. So yeah, one way to go is study what kind of symmetry is here. And also, we wonder if this construction can be generalized for the non-abelian anyon cases. And finally, our result for the four-partite chirality implies that there may exist some measures, like four-partite measures that can capture the chirality of the stabilizer state, which cannot be done by the usual modular commutator. So it'll be very interesting if we can come up with such measures. Okay, this is the end of my talk, and thank you for listening.
Thanks very much for the great talk, and we do have time for questions. Campbell.
Right. So here I use the anomaly to say that the string operator doesn't have a string operator. If you cut the string operator, that its topological spin is not 1. So since it's a fermion, so it's a anomalous symmetry.
Maybe you said, but I was wondering, from like a practical perspective, do you expect to encode some sort of information into the chirality that's sort of modest and constrained on?
Yeah, that's a great question. And I think one of the reasons why we still want to study topological phase for the quantum computation purposes is because we expect the different defects in the topological phases may correspond to different logical gates. So for the chiral phases, there may be some gates that we can realize for the qudit systems, but we don't have any concrete.
Have you thought about using these like XYZ choice of the gauge color generators to try and get like a Fourier code by switching?
Oh yeah, that's a great question. And I think we can view these XYZ choices as what happens for the dynamical codes in space-time picture. So we start from the color boundary, and then we can think of the different measurement, the two-body the gauge operator of the dynamical process as some kind of the pocket terms that is orthogonal to the plane. And then we realize the different instantaneous stabilizer group, the different levels of the boundary. Does it make sense?
Does it work to give you like a 3+1D Fourier code?
No, it's more like the 3D version of 2+1D dynamical coordinate. Yeah, but yeah, that's a great.
So mapping every ground state to a space-time.
Yeah.
2+1D.
Yes.
So, excuse me. So at one point you said you're able to conclude that the bulk has a finite temperature phase transition.
Right.
I was just wondering if you could expand a little on what the nature of that transition is between what kind of.
Right.
Is it just directly to some trivial state, or like what's characterizing that?
Right. So here the transition is given by if we can write down the density, the Gibbs state of the model as some convex sum of the trivial state. So under some temperatures, actually there's no, the Gibbs state becomes the long-range entangled, meaning that there's no way to write down as convex sum of the short-range entangled state. But and that temperature actually corresponds to the temperature that we can correct the all two-form symmetries, anomalous symmetries in this model. And it's like the pocket terms on the 3D toric codes, and it has some like finite temperatures of but the difference is that it's the anomalous symmetry, so it should be long-range entangled.
Another question? Yeah. So I have another question about the bulk. So the statement is that for some of these models, you've got chirality on the surface.
Right.
So does that mean the bulk has to have some sort of vorticity, or like what's the nature of a bulk that has a chiral?
Yeah, that's a great question. And I expect, even though the bulk is short-range entangled, I think it somehow encodes the information about the chirality on the boundary. And if you really think about the ground state of the bulk, and we can think of it as some superposition of the loop excitations, which corresponds to the chiral anyons in this model. And I think there might be the way to extract this information just by the 3D bulk wave function, but yeah, we don't have it.
Well, if there's no further questions, let's thank our speaker again.